board, which is almost always what we're going to use in here. But this generalizes. If you had a chain of k generalized eigenvectors, that's the kind of solution it produces. Theorem from linear algebra: any matrix, for any matrix, there exists a Jordan basis, all right, which is formed from joining together these chains of generalized eigenvectors. You can always find a set of n linearly independent vectors and or the real and imaginary parts of their complex generalized eigenvectors, which forms a basis for the matrix. And with respect to such a basis, we know how to construct solutions because we can use the magic formula like so. And that's how to unravel the formula. But I think we should look at something with numbers now before it's too late. So it may already be too late. Nope, I got 10 minutes. That's enough. Let us go back and solve the 2x2 problem we could not finish before, given our newfound technology. Looks like the non-homogeneous problem is going to have to wait for next class. That's okay. Oh, before I forget, I'll take attendance. Just write your name, if you don't mind. Joseph here? Other Joseph. John? I saw John. Yeah. You exist, there you are. Robert? Full house, but not that full. Mr. Kim? Oh, there you are. Jake? And back to Joseph again. All right, well, I tried. Okay, so if I could remember the problem, that would be something. Can you guys tell me do you guys remember the specific problem with 2x2 matrix that we couldn't complete the solution for? There was just one eigenvector. I guess I'll have to look it up. I can make one up, but when I make one up, it's boring. Did you find it, Taylor? No. It was from the part where I was scrolling. It's like, I think maybe at the start of when I was scrolling. All right. So just to give you a sense of, computationally, we have a game plan, right? We find all the eigenvectors we can, and then past that we look for generalized eigenvectors, and we use the sort of formulas I just derived for you, the magic formula and the red, or the formula I wrote just last, to construct solutions in view of those. And what I'm claiming for you is there's always enough vectors to put together a full solution set using these. All right. Oh, goodness gracious. I actually have the proof that e to the a to b is equal to e to the a times e to the b for a and b commuting in the notes to like arbitrary order. I forgot that's in there. Page 153. Goodness gracious. I'm a glutton for punishment. All right. The magic formula is also derived on page 155, although that may be page... No, it is 155. All right. All right. So I'm returning to example 5.44, which was 3, 1, minus 4, minus 1. 3, 1, minus 4, minus 1. This was the 2x2 matrix A, which we only found one eigensolution for. Let's work it out again. 3 minus lambda, 1 minus 4, minus 1 minus lambda. What do we got? Lambda minus 3 times lambda plus 1 plus 4, which gives me what? Lambda squared minus 2 lambda plus 1, also known as lambda minus 1 squared. So we have, by the way, this is example 5.5.7 on page 157 I'm currently working through. Now, so we have eigenvalue, lambda equals to 1, with algebraic multiplicity, what? 2. Then we look at a minus, let's see here, a minus I times u1, and we try to solve that to look for our eigenvector with eigenvalue 1, right? What is a minus I here? This is, looks to me like a 2, a 1, a minus 4, a minus 2, times my eigenvector uv. So can you guys tell me what that says that u1 should be equal to? Let me tell you a secret. You don't actually have to solve the equations for the 2 by 2 problem. What you're really looking for is simply a vector which is perpendicular to the rows. How do you find a vector which is perpendicular to the rows? Invert? Kind of. You flip the components over and put a minus on one of them. So I flip the 1 and the 2 to 2 and 1 and put a minus here. That should work. Check it. This times that gives me, oh, I didn't flip them, did I? I must have flipped them 2 times. Oops. Let's try that. 1 minus 2, rather. Check your answer. So this times that gives me 2 minus 2, which is 0. And then when I take the multiply that times that, I get minus 4 plus 4, which is 0. So indeed, this is an eigenvector. That's a shortcut. If you're calculating the eigenvector, you can think of it as the problem of finding a vector which is perpendicular to all the given rows in your matrix. This is sometimes a useful way of thinking. If you're comfortable with the idea of finding perpendicular vectors, it's useful. If you're not, then forget about it and solve the equations. But there it is. So our geometric multiplicity is, what is it? 1 for lambda equals to 1, right? There's just one eigenvector. So what we're going to do is we're going to look for generalized eigenvector. And we're going to solve the chain equation, a minus I u2 equal to u1. Now u1, we decided, I decided, I suppose, it's not much of a democracy in here. Sorry, I don't believe in mobs. You know, Republican and all. But apparently that's our new thing. I lose track. I just want people to get more upset about seatbelt laws, mostly. Like, why aren't people upset about seatbelt laws? Why do we have seatbelt laws? Like, what business is the government whether or not I wear my seatbelt, frankly? I see a thumbs up. I like that. That's good. I mean, I'm not saying I'm not going to wear it, but goodness gracious, if I want to drive from one part of the Walmart parking lot to the other without my seatbelt on, my car should not beep at me. That is obnoxious. But anyway, I digress. Okay, so the cool thing about this is this matrix we have already calculated. It's that matrix, right? So we're trying to solve the equation 2, 1, minus 4, minus 2. And we're looking for this vector uv that solves like that, right? We're looking for a non-zero solution as well. So what equations do we face? We face 2u plus v equal to 1. What's the second equation here? The second equation is minus 4u minus 2v equals to minus 2. It's the same equation again, right? There are infinitely many solutions possible, but let's pick one. What do you guys suggest we do? Now, in the previous case, I could not have made u or v 0. If I made either u or v 0, it forces the other one to be 0. In this case, I might as well make u equal to 0, right? Is a nice choice because v is equal to 1 there. And therefore, my generalized eigenvector of order 2 is 0, 1. And so by the derivation we went through today, e to the ta times u2 is equal to e to the t times u2 plus t times u1. Because we have a generalized eigenvector of order 2. And that's all that survives in the magic formula, just those two terms. But we can be more explicit, right? What is this? This is equal to e to the t times what was u2? Was 0, 1. What? And then I've got plus t. My u1 was what? 1 minus 2. So that is the solution that we were missing. What's the general what's the solution to this problem then? Let's write it down so we can stop for today. So what we have then is the solution is r is equal to c1 e to the t times my 1 minus 2. There's my eigensolution we learned about last class. And then I've got c2 e to the t times what? Well, I could put this together, right? If I put the thing in big parentheses over here together, I've got what for my first component? I've got a t, right? In my second component, I've got a 1 minus 2t. And there you go. That's the general solution to this 2 by 2 problem. We have now covered how to solve any 2 by 2 problem. It's either distinct real, it's repeated, and you need to look at the possibly get the generalized eigenvector order 2. If it's not a generalized eigenvector and it's repeated, that means the matrix is diagonal, which are really easy to solve. Or it's complex. Those are the three cases: complex, distinct real, or generalized eigenvector. I guess the fourth case is diagonal, fine, but that's so silly. I never ask about it. And there's the solution. Do you notice that when the eigenvalues, so something I would point out, when the eigenvalue is repeated, we don't just multiply by t, right? You can't just multiply by t. That's not what happened here. It's kind of complicated how the t enters in. It enters in through this magic formula business, right? It's a little bit more complicated. But nevertheless, we can handle it. We can do it. So I'll shut up, and I should go think about your quiz, right? So. In China, you can ride down the road with somebody on your handlebars in front of you, neither one of you wearing a helmet. It's allowed in China. There are many freedoms in China we don't enjoy here. It's true. I mean, religious freedom, not so much, but other kinds of freedoms, there are many in China. I was kind of surprised when I visited. Wait a minute, I thought I lived in the free place. I'm not so sure, though. I don't know. Depends on what kind of freedom you're interested in, Did you stop it already?
Nope.
Ah.